Uh, Welcome all of you. Am I audible to everyone?
Yes, sir.
Uh, is it visible, this slide?
Yes, sir.
Okay. So, I'd like to discuss the RISC processor. This topic is based on the RISC processor. And before introduction about the RISC processor, I need to discuss something about the CISC processor. Okay, CISC, 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 and another is RISC processor. So there are two types of architecture based on the instruction set, which is CISC architecture and a RISC architecture related processors. Okay, so CISC means the complex instruction set computer, and RISC is the reduced instruction set computer. Okay, so there are two types of computer architecture, and nowadays these RISC and CISC processors are made. That's why it is very important to know, or you need to gather some knowledge about the RISC processor and the CISC processor. Okay, and according to your syllabus, I'd like to discuss about the brief idea about a RISC processor only. Okay, so actually in CISC processor, what happened, the processor actually it used very much before invention of this RISC processor or RISC architecture, and more and more sophisticated processors were designed and marketed using that CISC processor, which resulted in an increase of processor die size to accommodate the large microcode required by the complex instructions. Hmm. So, and this large die size in turn, which means that more cost, uh, since it consumes more silicon, okay, to fabricate that processor. And also, as the chip size increases, the power consumption is also increases, and resulting in more heating of the chip. So this in turn requires more cooling arrangement. Okay, now if we use processors which support a set of simpler instructions which do not require complex decoding, then the design of the processor becomes simple with an associated reduction in cost and also the power consumption, and the execution also of these instructions will be very fast. Okay, so as the name implies, the reduced instruction set computer, or RISC, as it is properly known, is a type of architecture that utilizes a small, highly optimized set of instructions rather than a more specialized set of instructions often found in other types of architecture like CISC. And typically every instruction is executed in a single clock after it is fetched and decoded. Now these instructions are executed very fast. Okay, and a lot of disk space is consumed by microcoding, which is performed in a CISC processor, which could be otherwise used for enhanced feature also. It is thus possible to produce more RISC processor per silicon wafer. So that's why this makes a RISC processor smaller with lesser power consumption or energy consumption. Okay, so what is the history of that RISC architecture? Last day I have discussed some of these uh, introduction features about the RISC, but it was not completed. So it is pending. But today I have started from the initial position. Okay. And if you have any queries, any doubts relating to this, you can ask me after delivering my lecture. So the history about this RISC processor is, the first IBM was the company which defines the RISC architecture in 1970s. Okay, and this RISC related architecture related research was carried out or developed in the uh, University of California, Berkeley. Yeah. And also the Stanford University. So there a RISC processor has been invented, and it is applied to the computer architecture concept. So basically, RISC can be described. It's a philosophy of three basic levels. First is all instructions will be executed in a single cycle. Memory will only be. Second is the memory will only be accessed via load and stored instruction. And third is all execution units will be hardware with no microcoding. Okay, so basically, hardware is assembled to execute the instructions, which is very simple instructions, not the complex instructions. So actually, RISC here the instruction set is the hardware language in which the software tells the processor what is need to perform, and it reduces the size of the instruction set by eliminating certain instruction based upon a careful quantitative analysis, and requires these instructions to be used in the emulator. Okay, which can lead to higher performance, and that's why this architecture is followed everywhere nowadays. So it has certain features. Okay, like basically in RISC architecture the instructions are handled in this way. First fetch the instructions, then get the arguments, and then perform that function, and then write back the result into some register, uh, okay, so these are the steps how the instructions, simple instructions, can be handled. Now another viewpoint was that processor currently use a 32-bit data bus anyway. Okay, so why not make every instruction which is 32 bits in size? So every instruction cycle fetches 32 bits. Okay, and using this 32-bit efficiently make it logical to use 1 byte to code the actual instruction, and other 3 bytes to code the register to action. Like as for example, here one example is given as, suppose it is written as add r0 comma r1 comma r2. Okay, so here you need to perform the addition as well as the result must be written inside another register. Okay, like all of you know, you have performed the 8085 8086 microprocessor operations to perform any addition. Like in that case you need to add two register contents, and you have to store using the first register as your destination point. Here you can use three registers where the first register used as your destination point, and the another two registers are used to operate that function. Okay, so add r0 comma r1 r2 comma r2, which means that r0 that is the value which is loaded inside r0, which is equals to the r1 plus content of r1 plus content of r2. So two register must be added here, and the result will be stored inside r0 register. So that is so simple instruction which is used in the RISC architecture. Now there are different advantages of RISC architecture, so I will discuss one by one. The points are written here as first is the simple instructions. So the RISC instructions being simple can be hardware, while CISC architectures may have to use microprogramming in order to implement complex instructions. Okay, so according to every advantage I will discuss the difference also between the RISC and CISC. Okay, so do you have pen and paper with you? If you have, you can write it down. Okay, so simple instruction is performed in RISC, whereas in CISC architecture, the instructions are related to the microprogramming structure or microcoding structure. The next, so a set of simple instructions in RISC results in reduced complexity of the control unit and the data path. So as a consequence, the processor can work at a high clock frequency and else the higher speed. Okay, so uh, as a result, several extra functions like such as uh, so extra functions placed on a chip means extra function means the memory management unit or the floating point units are also placed on the same IC. Okay. Then the minimization of design cost, like the smaller chip allows the semiconductor manufacturer to place more parts on a single silicon wafer, which can lower the part chip cost dramatically. Okay, and here high level language compilers produced more efficient codes in a RISC processor than its counterpart in CISC processor, because they tend to use the smaller set of instructions in a RISC computer. Okay, so that's why efficient uh, execution is performed in RISC. Then it has a shorter design cycle. So a new RISC processor can be designed, developed, and tested more quickly, since RISC processors are simpler than the corresponding CISC processor. Okay, and easier to develop code for a programmer, where the application programmers who uses the microprocessor's instructions will find it easier to develop code with a smaller and optimized instruction set. And which is and another advantage is that the loading and decoding of instructions in a RISC processor is simple and fast, as it is not needed to wait until the length of an instruction is known in order to start decoding. Now, decoding is simplified as opcode and address fields are located in the uh, same position for all instructions here. Okay, so these are the advantages of RISC processors. Then some basic features of RISC processors are it has the simple instruction set. Um, so in a RISC machine, the instruction set contains simple basic instructions from which the more complex instructions can be composed. So thus instructions with less latency are preferred in this case. And same length instruction is used here. uh, Now each instruction is of same length, so that it may be fetched in a single operation. Now the traditional microprocessor from Intel to other manufacturer like Motorola supports that variable length instructions. Okay. Then it has single machine cycle instruction. Most instructions complete in one machine cycle, which allows the processor to handle several instructions at the same time. Okay. Now RISC processors have unity clock per instruction execution speed, which is due to the optimization of each instruction on the CPU, and massive pipelining embedded are used in the RISC processor. Okay, so pipelining here usually it is embedded in a RISC processor, so that is the key actually, which speed of the RISC machines. Okay, very low addressing modes and formats. Unlike CISC processors, where the number of addressing modes are very high, in RISC processors, the addressing modes are much less and it supports few formats. Okay. The large number of registers are also there, like the RISC design philosophy generally incorporates a large number of registers to prevent in large amounts of interactions with memory, because register to register operation is so fast, uh, much faster compared to the memory operation. Okay, so large number of registers are incorporated into this process, and microcoding is not required, like unlike in a six machine. In the RISC architecture, instructions microcoding is not required. This is because of the availability of set of simple instructions, and simple instructions may be easily built into the hardware. Okay, so maximum instructions are built into the hardware concept. So Then load and store architecture is there. The RISC architecture is primarily a load and store architecture, which implies that all the memory accesses take place using load and store type operations. Okay, so these are the basic features of RISC processors. Now there are some design issues related to RISC processors, like register windowing, like massive pipelining is there, like single cycle instruction execution, and the performance issues in pipelining systems are there. So these are the issues, and like to design this RISC processor, we must, or the designer must follow some certain rules, and this these issues can be fixed before performing before implementing that RISC concept into a processor. Okay, so what is the register windowing? The concept of register windowing involves a mechanism where the chips expose 32 registers to the programmer at any one time, but these registers are just a window into a larger set of physical registers. Okay, the additional registers are hidden from view until you call a subroutine. For example, like in other like in this processor, like for example the spark sun spark processor is an example of RISC processor. So in that processor, what happens, uh, like push instruction is there. So push parameter on a stack uh, for the call routine to pop off, they in that processor they just use the rotate the register window to give the call subroutine a fresh set of registers. The old window and the new window register are overlap, so that some registers are shared. And as long as you are careful about placing the parameters in the right registers, the windows are a slick way to pass operands without using the stack at all. Okay, now slick means the registered windows have their certain drawbacks. What is that? The like registered windows only help up to a point, like the number of physical registers are finite, and eventually it is runs out of space of more for more windows. Okay, so when that happens, you are back to pushing and popping operands on and off the stack. It's next to impossible to predict when the register file will overflow or underflow, so performance can be unpredictable. And finally, the processor doesn't handle the overflow or underflow automatically in hardware. Now it generates a software fault which the operating system has to handle, consuming more cycles. Okay, now many hardware engineers are not particular fans of this register windowing. It just puts enormous demands on multiplexers and register ports to make any physical register uh, appear to be any logical register. Okay, that register windowing actually, which is an inherent and permanent feature of every RISC type processor, has so far made it impossible to add multi-threading and difficult to keep clock speeds up. Okay, so that's why these design issues should be maintained properly, particularly for the register windowing concept. Okay, and then the massive pipelining issue is there. A RISC processor pipelining operates in much the same way, although the stages in the pipelining are different. While different processors have different number of stages, they are basically variations of the 5 stages, and the 5 stages are thus here. It fetches the instructions from memory, then read registers and decode the instructions, then execute the instruction or calculate an address, then access an operand in data memory and write the results into a register. Okay, now there are, however, the problems relating to the pipelining. In practice, RISC processors operate at more than one cycle per instruction. Now the processor might occasionally stall a result due to data dependencies and branch instructions. Okay, a data dependency occurs when an instruction depends on the results of the previous instruction. A particular instruction might need data in a register which has not yet been stored, since that is the job of a preceding instruction which has not yet reached that step in the pipeline. And in case of branch instructions, that instruction in that case, those instructions which instruct the processor to make a decision about the next instruction to be executed, depending upon the whether the condition is satisfied or not. So a branch instruction can be troublesome in pipelining if it is conditional and may be taken which has not yet finished its path through the pipeline. So in these two cases, it is much important to call this or to fix these issues. Then single cycle instruction execution is there. So in a typical pipelining RISC design, each instruction takes one clock cycle for each stage. So the processor can accept one new instruction per clock. Pipelining doesn't improve the latency of the instructions. Means uh, each instruction still requires the same amount of time to complete, but it doesn't. It does improve the overall throughput. Okay. Now, as with RISC processors, the ideal is not always achieved. Sometimes pipeline instructions take more than one clock to complete a stage. And when that happens, the processor has to stall and not accept new instructions until the slow instructions has moved on to the next stage. Okay. Idling of RISC processor means the processor remains idle when stalled. The designers of RISC systems employ several techniques like to avoid the idling of the CPU. And the RISC concept has basically led to a more thoughtful design of the microprocessor. Among design considerations are how well an instruction can be mapped to the clock speed of the processor, how simple an architecture is required, and how much work can be done by the microchip itself without resorting to software help. Okay, maximum this will be processed by the hardware. And the next design issue is based on the performance issues in pipeline systems. So now a pipelining processor can stall uh, for a variety of reasons, including delays in reading information from a memory, or a poor instruction set design, or dependencies between instructions. Now the question is how to address these problems. Okay, so basically there are two ways. One is instruction latency issues, and dependency issues must be addressed to overcome these problems. Why? Because memory speed issues are commonly solved using caches. Now a cache is a section of fast memory placed between the processor and the slower memory. When the processor wants to read locations in main memory, the location is also copied into the cache memory. Now, subsequent references to that location can come from the cache, which will return a result much more quickly than the main memory. Now, caches present one major problem to system designers and programmers, and that is the problem of coherency. Okay. Uh, I think all of you are not familiar with the computer architecture where this cache memory has been considered, and there are lots of issues. There are lots of design concepts has been incorporated. One thing is the problem of coherence. Okay, and I think I have a certain amount of discussions I've done uh, when the cache memory is there. I have already discussed the cache memory where the uh, locality of uh, reference has been there, or this type of concept. So when the processor writes a value to memory in cache, so it's basically present one major problem. Or what is the problem? And when the processor writes a value to memory, the result goes into the cache instead of going directly to the main memory. Okay, now therefore special hardware usually implemented as part of the processor, so it needs to write the information out to the main memory before something else tries to read that location, or before reusing that part of the cache for some different information. Okay. So there are two issues relating to this pipelining: is the instruction latency issues. A poorly designed instruction set can cause a pipeline processor to stall frequently, and these so some of the more typical CISC instructions which have more instruction latency should be avoided, and these are actually the highly encoded instructions such as those used on six machine need complex decoders. This should be avoided. Another is the variable length instruction which require multiple references to memory to fetch the entire instruction should not be considered for inclusion. Okay. Third is the instructions which access main memory instead of registers are slow in execution, since a main memory is comparatively slow. And the fourth number is the complex instructions which require multiple clocks for their execution, such as floating point multiplication, should be avoided. Okay, so these are the instructions latencies should be avoided. Dependency issues, basically it is happened, so it depends on single point resources such as condition code register condition code register. Now if one instruction sets the condition in the condition code register and the following instruction tries to read those bits, the second instruction may have to stall until the first instruction's write completes. Okay. Now one problem that RISC designers confront is that because of improper choice of instructions, the processor's performance can really get degraded to a large extent, since each instruction takes some amount of time to store its result, and several instructions are being handled at the same time. Later instructions may have to wait for the results of earlier instructions to be stored. However, a simple rearrangement of the instructions in a program can remove these performance limitations from RISC programs. Okay, and these instructions are called the instruction scheduling. Okay. Another optimization involves loop unrolling. So instead of executing a sequence of instruction inside a loop, the compiler may replicate the instructions multiple times, and this eliminates the overhead of calculating and testing the loop control variable again and again. Now, compilers also perform function inlining, where a call to a small subroutine is replaced by the code of the subroutine itself. Now this gets rid of the overhead of call and return sequence. Okay, so this is only a small sample of the optimization which is available. So these are the design issues in RISC processor. Then next is the hazards of RISC processors. Okay, like these are the causes on the use of RISC processors. Now the transition from CISC to RISC design strategy is, however, not without its problem. Okay, now these points need to be considered while using a RISC-based system, and the software engineer should be aware of the key issues which arise when moving code from a CISC processor to a RISC processor. And the first one is code quality. Uh, the performance of the RISC processor depends greatly on the code that it executes. Now, if the programmer or compiler does a poor job of instruction scheduling, the processor can spend quite a bit of time for stalling. That means waiting for the result of one instruction before it can proceed with a subsequent instruction. Okay, so that is the code quality needs to be there. Then is the scheduling. Since the scheduling rules can be complicated, most programmer uses high-level languages such as C, C++, and leave the instruction scheduling to the compiler. Now, this makes the performance of RISC applications depend critically on the quality of the code generated by the compiler, and therefore developers have to choose the compiler carefully based on the quality of the generated code. The next is the debugging. Unfortunately, instruction scheduling can make debugging difficult, and if scheduling are turned off, the machine language instruction show a clear connection with their corresponding lines of source. However, once the instruction scheduling is turned on, the machine language instructions for one line of source may appear in the middle of the instructions for another line of source code. So, such an inter mingling of machine language instructions not only makes the code uh, is to read that code, it is very hard to read that code. It can also difficult uh, to using a source level compiler, since single lines of code can no longer be executed by themselves. Okay, and therefore many RISC programmers debug their code in an unoptimized and unscheduled form, and then turn on the scheduler and hope that the program continues to work in the same way. Then next is the code expansion. Since CISC machines perform complex actions using a single instruction, whereas RISC machines may require multiple instructions for the same action. Like code expansion that had been compiled for a that can be a problem. That can be a problem. Now, code expansion refers to the uh, increase in size which results from a program uh, that have been compiled for a CISC machine. Okay, fortunately for us, the code expansion between 68 kilobytes of processors used in the non-power PC, like IBM Power PCs are there, so it is there to use that code expansion technique. Last one is on-chip cache. RISC machines actually requires very fast memory systems to feed them instructions. Now, RISC-based systems typically contains a large caches, usually on the uh, on-chip itself. Okay. So these are the difficulties when the code has been transferred from CISC to RISC processor. So why so which processor will I use and how should I choose it? It depends on the applications and certain specifications like high speed of data transmissions or real-time processing is to be controlled or not, or controlling certain specific applications. So based on this you need to choose which processor you need to use. Okay, so that's why the RISC has certain features, this kind of features, and that's why it is very much used nowadays. So you need to remember that reducing or simplifying the instruction set was not the primary goal of the RISC architecture. It's a side effect of techniques used to gain the highest performance can possible uh, from available technology. Okay. So the last slide is basically between the difference between the CISC and RISC processor. So CISC processor, the large number of instructions from 120 to 350 instructions are used, whereas in the RISC it is relatively fewer instructions, less than 100. In CISC processor employs a variety of data types and a large number of addressing modes have been formed, whereas in RISC it's a fewer addressing modes are there. and in CISC variable length of instruction is available, whereas RISC has the fixed length of instructions, usually 32 bits, and it is easy to decode that instruction format because all the instructions are in same format. CISC instructions manipulates the operands residing in memory, but in RISC mostly register to register operations, and the only memory address access is through explicit using load and store instructions. In a 6% number of cycles per instruction CPI, which can be varied from 1 to 20 depending upon the instructions, but in RISC it is number of CPI is 1 as it uses pipelining. Now pipelining in RISC is optimized because of simple instructions and instruction formats are available. CISC in general purpose registers varies from 8 to 32, but no support is available for the parameter passing and function calls, which is in macros and procedures available. In RISC, large number of general purpose registers are available that are primarily used as global registers and as a register based procedural call and parameter passing stack that's optimized for structured programming purpose. You need to use register, lots of registers are involved. And CISC microprogram control unit is there, but in RISC it is totally hardware control unit. There is no microprogram control unit is available. So this is the difference between CISC and RISC, and that is the brief introduction about the RISC processor. Okay, and that's all for today. So if you have any queries, you can ask me now. Do you have any queries?
Sir, whether you continue in next lecture or this is
No,
enough.
that's all for today. No next, no second session will be there. Okay.
Okay.
Can you tell me, do you have any classes on Saturday 4 p.m. onwards? Do you have any classes? Hello? Hello? Anyone? Can you tell me, do you have any classes from Saturday 4 p.m. onwards? Do you have any classes?
No, sir. No, sir.
Okay, if it's not there, then I think tomorrow I will take the last class of this semester, which is based on the ARM architecture, ARM processor. Okay, so I will I've not yet decided. So when it will be confirmed, I will give you the link of the meeting over Google Classroom. Okay, so you must check that link.
Okay, sir. Sir, hello.
Yes. Yes.
স্যার বলছি এক্সামের জন্য কি মানে 8085 থেকে 8051 অবধি সমস্ত
পুরো
আর্কিটেকচার মনে রাখতে হবে? সমস্ত মনে রাখতে হবে।
বেসিক্যালি তোমরা জোর দেবে 8085, 8086 and 8051। আর বাকিগুলো জাস্ট ওপর একটুখানি করে দেখে গেলে